Alright, so we're going to keep going with 3 response questions. This time we've got some projectile motion stuff to work on, coupled with collisions. So we're going to be determining the speed before a collision, displacement during the collision, velocity after collision, angle a hanging stationary object will reach after a given collision, and the period of the resulting oscillation when a dart is fired into a block hanging from a string, which looks like this. So we have a dart with a given mass. So we know the mass is 0.02 kilograms, launched at an angle of 30 degrees above the horizontal with an initial speed of 10 meters per second. The moment it reaches its highest point in the path, so this is the maximum height, is the exact moment when it collides with and sticks to a wooden block of mass 0.1 kilograms that is suspended from the end of a massless string. The center of mass of the block is 1.2 meters below the pivot point of the string. Center of mass is 1.2 meters below the pivot point. And the block and the dart then swing up until the string makes an angle of theta degrees with the vertical. Assume that air resistance is negligible, and we'll answer the questions below, starting with the speed of the dart just before it strikes the block. Okay, so we were told we are at the maximum height at the instant when we hit the block. So right before we start the block, what should our total velocity be? Okay, V equals, say one more time. Initial plus AT. So that would be looking at this one-dimensionally. V cosine theta. Okay, you're right, but why is it horizontal? Okay, so only when it's at the highest point of the arc, we don't have any vertical velocity. So that means all of the velocity is horizontal. Okay, cool. So it's not because of the collision, it's because we're at the highest point of the arc. Okay, so we've got our velocity is equal to our initial velocity, which you said was 10 times the cosine of 30. What's the cosine of 30? Not 1/2? Root 3 over 2, okay. So my velocity is a total of... What's our velocity? 5 root 3 units? Meters per second. Okay, perfect. So that's the speed of the object just before it strikes the block. Okay, next one. I think for AP Physics, they'll probably expect you to write that as a decimal. For your calculus exam, I'll want you to keep that as a radical. If I was going to write that as a decimal, this would end up being around 8.7 meters per second for my final answer there. But I'm going to leave it like this so that I don't round in other stuff for now. Okay, for part B, I want to calculate the total horizontal distance d, shown here. Oops, not pointing, shown here. Which is the horizontal distance between the launch point and the point on the floor directly below the block. What do I need to do? Okay, kinematics equation, we need to know the time first, so what can I use? Okay, cool. So Vy equals Vy initial, so that would be V sine theta plus AT. where that, what is this A? Okay, that's really G because we're looking vertically. Okay. So we've got, okay, yes. Because we won't have any vertical velocity at the time we want. Okay, I'm going to use 10 for gravity, I guess. So 10t. And that should be, yeah, it should be negative. Okay. So I need to solve for t. 10t equals, what's 10 sine 30? 5. So t is, okay, at half a second after we launch, we will hit the block. So now that I know how much time we're in the air for, how can I use that to figure out our distance? Okay, so that was 5 root 3 times the time of 1/2 is 5 root 3 over 2. Perfect. What are our units? Which would be around 4.4-ish, since my rounding's a little bit different here. Okay, any questions on A or B? Okay. So kind of pre-calc projectile motion so far. We're going to keep going for speed of the block, and then we swap over to physics. So what do I need in order to figure out the speed of the block just after the dart strikes? Conservation of momentum. So momentum before must equal momentum after. Okay, so you're right, 0.02 times our initial velocity is not just 10 though. 5 root 3. Okay, equals both masses. VF, okay. So this is 2 over 100, so I've got 2 over 100 by 5 root 3 is equal to 0.12 VF. Okay, so therefore 10 root 3 is equal to 12 VF, where VF equals 10 root 3 over 12 is 5 root 3 over 6. Which, if we solve, ends up being around 1.4-ish. Okay, any questions on C? And part D? Okay, we're looking for the angle through which the dart and block will rise before coming to rest. Doing D, so delta. Okay, yes. Why am I using energy? What do we need? Okay, not quite, but we're gonna have some kinetic energy in the start. All that kinetic energy will convert to potential energy when we're at the top of this arc here, right? But if we know what the potential energy is, we can figure out what that change in height would be. And then we can use that change in height to figure out what the angle is. Okay, so I'm going to draw this out really quick. We've got something that looks like this. So after the block stops, we'll be here. Okay, so we're going to start out with some kinetic energy. And there won't be any potential energy. We'll move up to here along the arc, where we'll end up with no kinetic energy and some potential energy. This distance here in yellow will be h. And if this distance, this whole distance here in, I'll do green, is the length of the string, then that would be this length. So in terms of L, what is H? That's it. That's what I was getting at. L minus L cosine theta. Okay, so I'm going to use what you just set up with your potential energy equation, and we'll combine with this and see what happens. So this is conservation of energy. Our initial kinetic and potential must be equal to our final kinetic and potential at any point. We started out with only kinetic energy, so what would our kinetic energy be? Okay, and then what's my potential energy at the end? Okay, you're right. All right, so we've got 1/2 mv squared and mgh. So this is v squared over 2 equals g L minus L cosine theta, right? Okay, I want to get cosine theta alone. So I'm going to divide by g and divide by L. So this will be v squared over 2gl is equal to 1 minus cosine theta. Agree? Okay, I'm going to subtract 1. So this is v squared over 2gl minus 1 equals negative cosine theta. Divide by the negative 1 will change my signs. So that's 1 minus v squared over 2gl equals the cosine of theta. Or 1 minus 5 root 3 squared over 2 by 10 by 1.2 equals the cosine of theta. And I'm going to go to the calculator there. You're right. Okay, so this is the velocity of both, not just the velocity of the dart. Awesome, thanks. Okay, so this will be 5 root 3 over 6. Okay, that's what I was missing the first time. Okay, so this will be 1 minus 5 root 3 over 6 squared over 20 by 1.2. Okay, and that's in range. Second arc cosine of answer gives us 24 degrees. Okay. I'm going to write degrees because I can't tell whether it's a 0 or a degree sign with this. Any questions on D? I just messed up with which velocity I picked, I think. But I think you would have been fine there. Okay. So, party? Square root L over G, okay? Okay, that L is the length of our string. So that's 1.2 over 10 for us. Okay, then what do I have to do after this? Okay, the time would be period over 2. Okay. Then for the last one, if we launch a dart with more mass at the same speed and angle, would the angle increase, decrease, or stay the same? Okay, you're right. Why? Say that one more time. Mm-hmm. You're saying a more massive dart will have larger speed. Is that what I heard? We could put any dart of any mass at any speed, right? So As long as I'm firing the dart, regardless of the mass, at 10 meters per second at that 30-degree angle, it's still going to have all of the horizontal speed when it reaches the maximum point, right? So its horizontal velocity right before it hits is going to be the same, v cosine 30. Okay, so that's not y. Let's look at what happens to the speed after the collision, though. So, how did you get your speed after the collision? Before that. Momentum. Okay, that momentum is because we used momentum to figure out what the velocity of the dart block system was. You're going to have more momentum with more mass at the same velocity, right? That's why. Okay, so when using a more massive dart, the angle should increase because the momentum, of a more massive, of larger. Transferring more velocity after the collision. Okay, does that make sense? Okay, we have a greater speed after the collision because we had more mass. So when we conserved our momentum from the dart into the dart block system, we ended up with more velocity. Okay, that was part A. F part B. Would the period of oscillation increase, decrease, or stay the same? Okay, you're right. Why? Awesome. That's perfect. Okay. Any questions on anything from this one? Okay, I'm going to keep all our annotations and save that again. So we've got it available for notes later. And we should be good to go. So I will see you tomorrow for Calculus BC.